electric currents and related. Okay, then in chapter 25, we have the topics and the quantities that we are going to discuss: current, resistance, and electromotive force. Then all these three, we are going to study the meaning of each, how to calculate, and how they are really related. Now, of course, the learning goals for this chapter, what does it mean electric current and how charges move in a conductor? And here we are going to introduce, I will say, maybe 2 methods or 3 to calculate currents. And also by chapter 26, we're going to add more methods. How to calculate the resistance of a conductor from its dimensions and its resistivity or conductivity. Then we are going to define resistivity, we are going to define conductivity, and we will also know how to relate these to resistance and to calculate the resistance. Also, how an electromotive force, which is for abbreviation we're going to use for it, lowercase EMF, makes it possible for current to flow in a circuit. How to do calculations involving energy and power in circuits, because this is one of the ultimate goals that we are looking for always. I want to design any electrical network, and then I'm really interested in calculating power and energy. How to use a simple model to understand the flow of current in metals. These are really good conductors. Now, what's the difference between what we have studied so far and what we're going to study today is that we are going to study today charges in motion. Then when I say I'm going to study the electric current, I am talking about charges in motion. Then I will say this flashlight that the kid is really holding, having some kind of charges that they're gonna move and they're gonna flow and they're gonna go through the bulb, and they are going to to make that bulb glow. Also, it is the energy of the charges that decreases as the current flows through the light bulbs, and then I will say they're gonna go back to the battery so that they will get more energy. And also we need maybe to focus more on circuits, which are really networks, or some of kind of the electronic components that we are going to put together, and they are really constituting the heart of modern devices like computers, televisions, and all systems that we can see around. Now, a current at any instant can be defined as the motion from one region to another. Then here we have remember, positive charges, they usually flow in the direction of the electric field, and they are really moving, they are really aligned because of the electric field. Before the electric field, they're gonna be moving in all directions randomly, but here they are really moving in the direction of the electric field. They are really aligned. And one thing that we need to understand, that actually what is really flowing, it's not the charges, the positive charges. These are really the electrons, which are the current carriers. But for simplicity, we are going to use the direction of the positive charges. Okay, and I will say each charge here is going to move with a velocity Vd. We call it drift velocity. Then this is really a very important quantity that we are talking about, which is the V drift. Now, the current can be calculated as charge per unit time. Which means it is dq over dt, which is coulomb per second, which is amperes. Also, I can calculate current using the other equation, which is having these variables. This is N, is the number of charges per unit volume. Q, it's the magnitude of the charge. And VD, it is the drift velocity. And A, it is the cross-sectional area of the wire. Okay, then here I will say, let me define this. This is like N, it is the number of charges per unit volume. Okay, then it is the standard unit for it, let's say electron per cubic meter. Q, it is the electronic charge. And we use for it, like sometimes you're gonna see that I will use for it E. And of course for the electron it is negative, but I'm interested in the magnitude. Okay, and also VD, we call it drift velocity, and that is meters per second. And finally area, it is the cross sectional area of the wire. And usually wires, they have a circular cross-sectional area. Then they have that area is pi r squared, or pi r d, the diameter, over 2 squared, which is d squared over 4. Now, for the direction of the current, the current actually now we are taking it the direction of positive charges. It can be positive or negative. We will have something called conventional current, which is the flow of the positive charges, and this is what we are going to use in this course. Actually the actual direction of the current, we call it the electronic current. It is from negative to positive, because electrons are the charge carriers, and therefore they're gonna be repelled by the negative, and they're gonna move towards the positive. And actually this was, I read once, I'm not sure like if this is true, that like the scientist who decided in the direction of the current, he just thought wrongly with the direction, and he made it from the positive, but this will not make any difference. Now also, we will say in general, conductors contain several different kinds of moving charge particles. It is, if we have an ionic solution, then we might find negative and positive ions moving. For example, in ACl solution, we will find Na positive and Cl negative. The total current I is found by adding up the currents due to each kind of the charged particles. We can define a vector current density that includes the direction of the drift velocity, and that is, we are going to call it J, and that J equals N times Q times VD. Then this is really the quantity that we call it current density. It is N, the number of electrons or carriers per unit volume, times Q times VD. And the vector current density is always in the same direction as the electric field, no matter what the signs of the charges carriers are. Then it is very convenient to use it. Also, we can define a new quantity. We call it resistivity. And that resistivity is the ratio of the electric field in the material to the current density it causes. And that rho here, we are using it, is going to be E divided by J. And the conductivity, it is the reciprocal of the resistivity, 1 over it. The next slide shows the resistivity of various types of materials listed for conductors, for example, like copper. It's 1.7 to 10 to the negative 8 okay, then it is the resistivity, it should be very low for conductors. Gold also is a good conductor. Lead also, it is an excellent conductor also, if you look. And I will say here semiconductors, they are in the middle. And then insulators, of course, they have large numbers for resistivity. Now, circuit boards and resistivity, of course, we are going to work with one of the boards in this coming lab, Coulomb's law. Now, we use usually copper wires because, of course, like it's cheaper and it has like other, I will say, good properties. They can be easily, making wires from, I will say, copper. Here on this circuit board, they are printed directly into the surface of the dark colored insulating board, and you can see that these lines here, the yellow ones, are really the copper. Even though the traces are very close to each other, the board has such a high resistivity that essentially no current can flow between the traces. And this is like all now we are using these, I would say, boards widely. Now you need to know that resistivity changing with temperature, then I will say the resistivity of a metallic conductor nearly always increases with increase in temperature. And this is because the motion of the carriers is going to increase with temperature. Over a small temperature range, the resistivity of a metal can be expressed approximately as a function of temperature. Rho zero here, which is resistivity at a reference temperature, TO, maybe room temperature or any temperature, and multiplied by 1 plus alpha, which is called temperature coefficient of resistivity. We're going to work on problems, including these, and multiplied by T time alpha T, the temperature, minus the reference temperature. Now here also we are listing temperature coefficients for of resistivity for aluminum, for carbon, for copper, for iron, for silver. Remember these numbers, you don't have to memorize. They will be given to you whenever needed. Now, the resistivity of graphite, which is a semiconductor, decreases with increase in temperature, since at higher temperatures, more electrons shake loose from the atoms and become mobile. Actually, we have them moving from a non-conductive region to a conducting material. This is the reason why we call them semiconductors. Semiconductors at room temperature without doping, they are really they are not good conductors. And then when we increase the temperature or add a doping, like another I would say element to it, is going to be a good conductor. Measuring the resistivity of a small semiconductor crystal is a sensitive measure of temperature. This is the principle of the type of the thermometer called thermistor. Okay, this is like just one of the applications. Also, some materials show a phenomenon called superconductivity, where they are going to be, I will say, as if they have zero resistance. And as the temperature decreases, the resistivity at first decreases smoothly like that of any metal, and below a certain critical, it will suddenly drop to zero. And once a current has been established in superconducting ring, it continues independently without the pressure of any driving field. And this is a very promising technology for trains and for maybe other applications. We can maybe we can talk about it later. Now, resistance and Ohm's law. resistance of a conductor can be defined as rho, as R equals rho L over L, A. L, it is the length of the resistor, and A, it is the cross-sectional area of the resistor. And the potential across a conductor is given by Ohm's law, V equals IA. IR, which is I, the current, times R, which is the resistance. Here also, we are going to also use this later, because it's easier. Maybe we're gonna have the resistors color coded so that we will be able to calculate their, values. And for example, here we can see that this resistor has a resistance of 5.7 kilo ohms with a tolerance of 10%. Now look here at the green, look at the numbers here. The first band, it's green, and green, if I will go here, it is 5. Now the second digit, it is the violet, which is 7. And then you're gonna say times 10 to when the multiplier, when it is orange is 10 to the 3. And the tolerance, it is silver or gray here, then it is 10 to the, okay, let me see the tolerance here. Yes, it is gray. It is 10 to the 8. Yes, mostly we use usually for tolerance, we use usually gold and silver. Okay, here, then this one, it is 557, 10 to 3. Okay. Or, wait, here I think there is a mistake. This is 5, and this is 7, the second digit, times 10 to the orange. Is it orange or yellow? It is orange. I can see it orange. I think they, okay, 10 to the 3, then if I will divide this by 10, I think there is a mistake in here, because this should be 57 kilo ohm. Okay, I am considering this to be orange. If it is yellow, then 57, 10 to the 4, yes, then it's gonna be 5.7 kilo ohm, but I can see it orange anyway. Okay, and for the tolerance, it is here, it is silver. It's not listed here, and it is 10%. For a resistor that obeys Ohm's law, if we will be able to do an experiment, and we will do, of course, an experiment, we will find that V versus I, or I versus V, is going to be a graph like this. I like always to say V over versus I, because I want to have my slope equals R. But here they graphed I versus V, then this is, the slope is going to be 1 over R. Any resistor that is going to obey Ohm's law, which means when you are going to plot its voltage versus I, is going to give you a straight line. We call it ohmic resistor, and at a given temperature, current is actually proportional to voltage. Non-ohmic resistors, all other devices are non-ohmic, and they don't obey Ohm's law. The relationship of voltage to current may not be a direct proportionality, and it may be different for different, situations. This is for a semiconductor diode, which is a component that we are widely using. In the direction of negative current and voltage, little current flows. In the direction of positive current and voltage, I increases nonlinearly with V. Here, whenever we're thinking of electric circuits, usually we are really comparing, I will say, electric circuits with water systems. Then here I will say, if we have here a water fountain, then it needs a pump, and also in an electric circuit we need a pump, and that is where we call it the source of electromotive forces, so that it will sustain a steady current. Now, the influence that makes current flow from lower to higher potential, it is called electromotive force, and we use for it EMF, lower cases, and a circuit device that provides EMF is called source of EMF. It can be a generator, it can be a battery, it can be a power supply. Now, electromotive force, it's a poor term because it's not a force, of course, but it is energy per unit charge quantity, like potential or voltage. The SI unit for EMF, it is volts or joules per second. Now, a typical flashlight battery has an EMF. All these dry cells that we are using, the AAA or the AA, they are all 1.5 volts. That means that the battery does 1.5 joule of work on every coulomb of charge that passes through it. Then it's gonna provide the energy for the circuit. We use for it, this script, which is capital E for EMF. Now, real sources of EMF, actually, they contain a small resistor. We call it internal resistance, and that is really as if it's gonna steal some of the voltage. And then I will say the terminal voltage of a 12-volt battery shown at the right is less than 12. This is because of the, that small resistor, which is the internal resistance, is actually holding, or like it has some of the voltage on it. Then VAB is going to be EMF minus IR. It's easier when we are going to draw circuits that we are going to use some of the symbols. For example, here, conductor with like zero, I will say, or negligible resistance is going to be just a wire, it's a straight line. The resistor, it is this one. The battery or the EMF, it is two lines parallel to each other, different, of course, from a capacitor, where they are going to have a negative and positive. This is a source of EMF with internal resistance R, and can be placed on any side. V here, we use it for voltmeters, which they are really used in parallel, and they have usually very high resistance, and ammeters to measure current, which is in series, and usually they have zero resistance. Now, potential changes, and also I will go over this in the examples. The figures show here how the potential varies as we go around a complete circuit, and I will say here the potential will rise here between this one and this one. The magnitude is 12, then it will rise from 0 to 12. And then it's going to be, because this is a wire, then it's going to stay the same. Now, the current is going through the resistor in this direction. Therefore, it's going to be a drop of this is the internal resistor of the circuit, is going to be IR, which is 4 volts. Why 4 volts? Because the resistor value is 2 and the current is 2, then 2 times 2 is 4. Then there is going to be a drop of 4 volts because of the internal resistance. Then this is like another resistor, the external resistor in the circuit. It has 4 ohms and then the current is 2, then it's going to drop another 8, and then we are going to go back to 0. Then this is really here showing you the drops in the voltages, but again going around all the loop, it brings the potential back to where it's gonna start it, and it's gonna be like, if you will go a complete cycle, is gonna be 0. Now here we have a box that represents a circuit element with potential difference that is VAB, that we are going to use it, and it has current I passing through it in the direction from A to B. If the potential at A is lower than B, then there is a net transfer of energy out of the circuit element, and that time rate, which is, remember, P, it is E over T, is going to be VAB times I. The upper rectangle represents the source with EMF E and internal resistance R, connected by ideal wires that they don't have any resistance, to an external circuit represented by the lower box. And here we can say that point A, it is at a higher because it is positive than point B, so that VA is greater than VB, then VAB is positive, and P, the power, it is VAB times I, and that is EI minus I squared R. Now, electrons in a conductor are really free to move through this crystal, colliding at intervals with stationary positive ions. And the motion, it is actually, I will say, random, without having the electric field. And the motion of the electrons is analogous to the motion of a ball rolling down an inclined plane and bouncing off pegs in its path, which is okay. And then when we are going to have the electric field, is going to be aligning them, and there is going to be the resultant is going to be the random motion plus the drift. Okay, I'm gonna stop here, and I'm gonna post another video for the problem solving. Thank you and have a great day.